Hi everyone, it's Miss B, and in this video we're looking at the Lesson 15 practice problems for Illustrative Math Algebra 1. And so this lesson is on inverse functions. So that's the focus of this practice. So question 1 here, we have Noah's cousin is exactly 7 years younger than Noah. So we want to let C represent the cousin's age and N represent Noah's age, and ages are measured in years. So we want to write a function that defines the cousin's age as a function of Noah's age. So we basically want to say C is the cousin, and what is that equal to if we use Noah? So what are the input and output of this function? So let's start by writing part of our function. So C equals. Now this is 7 years younger than Noah, which means Noah and his cousin's age are not equal. I have to actually subtract 7 from Noah's age to equal that of his cousin's. So our function is essentially C equals N minus 7. So in this case, the input is going to be Noah's age. And the output is his cousin's age. So Noah's age was N. Output, I was just checking that I was using the right variables. Cousin's age, which we're saying is C. Okay. So now we're going to look at the inverse of the function we just wrote. So to find the inverse, we're just going to intend to solve by putting the other variable by itself. So on this first one, C is on its own. It is quote-unquote solved for. We are now going to solve for N. So we want to end up with N equals something. So if we start with C equals N minus 7, we can work with the assumption that we want to get N by itself, and we can add 7 to both sides. Now what happens here is that these 7s cancel out because one's positive, one's negative. And what we have left on the left-hand side is C plus 7. And then on the right-hand side, we just have N. So if you feel better about it, you can always turn it around. I like to have my letter first, so I can say N is equal to C plus 7. Those are the same thing, but they both work. So now it's asking us what are the input and output of the inverse function. So in this case, the input is now going to be C. So the input is the cousin's age. And the output, or the one that's solved for, is Noah's age. Which is N. So the whole idea of inverse functions is that we are switching the input and the output and solving to find what the new function would be. Or if it is a function. Sometimes we'll get stuff that won't be. Okay, so let's keep going. We have more questions about Noah's cousin. So Noah's cousin is exactly 7 years younger than Noah. That's that same situation. We said let M represent Noah's cousin's age in months and N represent Noah's age in years. So now we can start converting a little bit. We had C plus 7 equals N, or C equals N minus 7. If Noah is 15 years old, how old is his cousin in months? So we want to find the cousin's age in months. Now if it was in years, this would just be Noah minus 7, but that's not true because they're not both in years. This is going to give us an answer that's in years, but we need to know how many months there are there. So I'm actually kind of doing step 3, or question C here. Um, but yeah, so let's, if Noah's 15, then that means so they're giving us Noah is 15. We can say his cousin then, who is 7 years younger, is going to be, what is that? That's going to be 8. And we know we can do 8 times 12, and this is 96 months. So this equation, not quite going to work. We have to actually find our years and then change them to months. Okay, so now when Noah's cousin is 132 months old, how old is Noah in years? Well, we're going to take that 132 and we're going to divide it by 12. So I don't remember if this comes out to a nice number, but we'll check it. So 132, we're going to divide that by 12. Ah, yes, it does. It's 11. I guess I don't know my 11 times 12. So that's going to be 132 dividing that by 12 equals 11 years old. But that for us is the cousin's age. So we want to know how old is Noah. So Noah is the cousin's age plus 7. So we can say Noah is 11 plus 7, which is 18 years old. But that is kind of a lot of work to just find some ages in months and years. And we're gonna make this a little easier. So to actually write this function, we want the output to be the cousin's age in months and the input to be Noah's age in years, because it does say it gives the age of Noah's cousin, and it is specifically in months. So we do want to have m be by itself, because the variable that represents the output is what we normally have solved for or on its own. So it's not just equal to n minus 7, because n minus 7 would be the years. We then have to take that result and multiply it by 12. So our function is going to be n minus 7 times 12. Now you could do 12 times n minus 7, or you could distribute that 12 through. But I like to leave it like this because it kind of makes more sense in my head. Now we want to write the inverse of the function. And then they're asking us what are the input and output. So in order to write the inverse, we want to get n by itself. So m equals n minus 7 times 12. I would start this out. Essentially, we're trying to move everything away from n. And so I can't do what's inside the parentheses with it first. We kind of have to do reverse PEMDAS. So the things in the parentheses get taken care of afterwards. So we work in backwards order of operations to isolate a variable, which means before I do anything in my parentheses, I need to take care of this multiplication by using division. So we're going to divide both sides by 12. And that would give us still just m over 12. But on the right-hand side, those are going to cancel, and we would just be left with n minus 7. We can add 7 to both sides, so 7 plus m over 12. That's going to be n minus 7 and then plus 7. And our goal is that those will cancel. So n is now by itself, but I'm going to put it on the left because that's the way I like to write these things. And traditionally, we put everything with the variable first, so I am going to put m over 12 plus 7, even though the 7 was first in my description there. So this is now my inverse function, which means the output is this n over here on the left. So I can say that my input is m cousins age in months, and the output is n Noah's age in years. Okay. And that's question 2. Not too bad. I guess for consistency, I will put my function here in a box, since that's what I was doing with everything else. So that way you can see what my solution is. So on to question 3. So question 3 here, we have 4 different equations. They're saying each one represents a function. For each, find the inverse. So let's zoom in here and see what we have. Oops. All right, so for our first equation, we have c on its own. So c is what it is solved for, which means w, the other variable, is now what we want to get by itself. And it looks like it just has something being added to it. So the inverse operation, or the operation that undoes addition, is subtraction. So we are going to subtract 3 and subtract 3. What this is going to give us left over is w on one side, and then on the other side, so I know I'm kind of doing this out of order because I'm switching their sides, but we would have c minus 3 left over on the other. I'm used to just writing the isolated variable on the left, but if you're more comfortable with writing c minus 3 equals w, that works too. And so that is this first part of the question. I'm going to alternate the colors of my work here so they don't end up bleeding into each other or being less readable, I suppose. For part B, we have y equals x minus 2, so we have subtraction going on. Just like subtraction is the inverse of addition, addition is the inverse of subtraction. So we're going to add 2 to both sides, because our goal is to now get the x by itself. So those 2's will cancel each other out, and what we would have here is x on its own, and is then equal to y plus 2. So we're just doing the opposite operation, basically whatever it undoes, to each side, until we have the other variable by itself. C and D are both one-step equations as well. They're using different operations here, though. So just like we had addition and subtraction, for C and D we have multiplication, and then we have division. So let's go back to using red. If y is equal to 5x, we want to get x by itself. So in order to do that, we're going to divide both sides by 5, because divide is the opposite of multiply. So we'll have this here. Cancel out. And then what's going to be left is x equals to y divided by 5. And this is the inverse of that one. Last one on this page is w. The w is equal to d divided by 7. But the nice thing is we know what the opposite of divide is. That is multiply. So for each side here, we want to multiply by 7 and multiply by 7. So on the right-hand side, the denominator of d is going to go away with that multiply by 7, because we're just undoing it. So d will be by itself, but then w times 7 is 7w. So we have d is equal to 7w. And there we go. We have 4 little answers here. Hopefully I zoomed in enough that you could actually see the work. But yeah, and that's all of question 3. So if we move on to question 4, for me that's on the next page, we have years and months. So we're going to have the number of years y as a function of the number of months m. The number of months m is also a function of the number of years y. We want to kind of write 2 equations, one to represent each, and we're going to explain why the 2 are inverses. So we're going to use y and m. First, let's write what a month is. The number of months. Well, we know there are 12 months in 1 year. So for every 1 year, I have 12 months, meaning if I was to plug something in for number of years, I would multiply it by 12 to get the number of months. And if I wanted to convert something from months into years and just have years be equal to my answer, I would take the number of months and divide that by 12. Okay, so there I have one function, or one function for each, but I have 2 equations. So m is equal to 12y, and y is equal to m over 12. And so our next step, I guess, is to explain why they are inverses of each other. Well, first off, I would say the input and output are reversed or swapped. So one of the key things that we use to actually create an inverse function is just swapping which is our input and which is our output, and we do that by isolating the variable. Now the other way is we're also going to talk about the fact that we are using, in this case, inverse operations. So the functions, and you'll notice we're saying inverse a lot for inverse operations. We're using the opposite operations to create inverses. So that's kind of where those words come from. We always have called addition and subtraction inverse operations, and multiplication and division inverse operations, but now you really get to see we do the inverse to create an inverse function. So the functions use we can say they're using the same the functions use the same number, which is 12, but inverse operations this is multiply and divide, which are inverses of each other. So it seems like it's cheating a little bit to say I'm using inverse operations when I'm talking about why something is an inverse, but that's, why it works. So the idea is we're using m and y and 12, but in one of them we're multiplying and in the other one we're dividing. And because our inputs and outputs are swapped, that's what's going to make sure that these are inverses of each other. Okay, so that brings us on to number 5, which is sketch a graph to represent each quantity as described as a function of time, and be sure to label the vertical axis. So we have a couple different things here. We have the swing, we have a slide, we have a merry-go-round and merry-go-round again. And so this is kind of review. It's from Unit 4, Lesson 8. We're just actually going to be sketching a graph here. So let's just look at the swing. So I'm going to zoom in on this one. This is the height of your feet above the ground while swinging on a swing at a playground. So there are a couple different things that it might mean. But we know that a swing goes back and forth. So as you're swinging on a swing set, right, you have your little swing hanging down here. You're going to be going up and then back down and back up the other direction and down and then back up again. So we are going to be getting higher above the ground and then back lower and then higher and lower, and we're never going to quite touch the ground either. So I might start with my swing a little bit above the ground because they don't touch the ground. And then I would probably increase and reach a maximum. And then I'm going to come back down and reach that minimum again. Now, the minimum is going to be the same as where the swing is when it's sitting still. So it's important that our maximums and minimums are essentially the same. So then we can go back up again, and then back down again, and back up again, and you get the idea. Although we can kind of leave it here because maybe, you don't get off the swing when it's up in the air. I guess you could. I think I remember doing that as a kid, but we'll just say that for safety's sake, you're going to get off the swing when it is down at the ground again. So that's an example of that. Now we have time. So this is maybe in seconds. And then this would be like feet off the ground. Or height. Let's call this height. Yeah, I didn't realize we called it height. I thought it was the distance of your feet off the ground. So height. And this is measured in feet. Okay, so we might say this is maybe like, I don't know, 1, and then like 2, 3, 4, 5, something like that. Sketch and describe is a function of time. Okay, so I was just double checking that I have everything I needed on here. So now we are on to sketching our slide. So our situation here is that the height of our shoes, so if we're standing on the ground, we're at ground level. The height of your shoes above ground as you walk to a slide, go up a ladder, and then go down a slide. Okay. So first off, I'm going to use a brighter color, so red here for this one. I'm going to walk to the slide, which means I am walking on the ground. So my line, I walked to it. I took some time there. There we go. But so it's really important that we do actually have a chunk of time where we are on the ground. Now, if we're walking up a ladder to get onto the slide, we're gonna basically be doing some steps here. So we're gonna be jumping a little bit of a. Is it reasonable for us to go straight here? We can go, because it takes time to step up, but not super long. We can say stepped up, and then we're on that rung of the ladder. And then we stepped up, and then we're on that rung of the ladder. And then we stepped up, and we're waiting on the ring of that ladder. Takes us a little while to get, your other leg up to the correct rung. Ladder. I don't know how many feet we want to give this. 1, 2, 3, 4. We'll give it one more think I gave my swing about 5 feet of height. And then we're on the ladder. Now, at the very top, then we might wait for a second, but then we're going to slide pretty quickly down. And that would take us all the way down to the bottom at a pretty constant rate. So that would be my graph for this one. So we can say time is maybe seconds. Or we don't maybe have to be specific, but we are going to say this is height. Because again, it is our height off the ground. You can label it, but we're not going to be super specific with our label. We're just going to say that it's height and time. Okay, for the merry-go-round, we have actually 2 instances of merry-go-round, but we're just going to look at the first one. It is your distance from the center of a merry-go-round as you ride the merry-go-round. Well, a merry-go-round stays in place and it spins around its center, and generally you don't move from the center of it. So I would say that this graph is probably just going to be a flat line for the entire time that you are riding it. So it did describe to me that it's as you ride. It's not like it doesn't involve walking up to it or anything like that. So we can actually just use a flat line for our whole graph. Okay. Now, what is this? This is distance from center. So we can say distance from center. Okay. Now the merry-go-round again is a little bit different. So your distance from your friend who is standing next to the merry-go-round as you go around. So let's just draw a picture here real fast for some sort of merry-go-round, an actual round shape. Miss B, come on. A circle. There we go. So maybe this is the merry-go-round. This is the center. It has like the little bars or whatever on it most times. We'll say they go like maybe one set vertical and one set horizontal like this. Okay. And then your friend is standing here. As we go around the circle, this is going to be the closest point that we are to our friend. But we're never actually going to be touching our friend because hopefully they're staying in a safe place, which is out of reach and not going to get hurt by the merry-go-round because we might like to spin it real fast. But as we move around the outside of this, over here, I'm actually going to be further away. And then the furthest I'm going to be from my friend is here. And then I'm actually going to begin to get closer again, closer to my friend. As I reach here, then I will be in the closest spot. So this is kind of like the swing question, where we're getting further away, further away, further away, further away. We reach our maximum distance away from our friend, and then we start getting closer and closer and closer and closer. And we're going to reach the minimum distance away from our friend, but never quite touch it. So hopefully that explanation made a little bit of sense. I am going to... We actually don't need to start this one at a specific spot, but I am just going to start it so that I'm not at 0. And we're going to have that same sort of pattern. So we would go increasing distance, decreasing distance, increasing distance, decreasing distance, and sort of have that pattern as we continue to ride. Now, my hand is not the most steady, but you get the idea. It should look kind of like our swing one. So, yeah. And then this was distance from friend. All right. So I believe that's it for that question. We're going to go on to the next page. And here we have question 6. So Lynn charges $5.50 per hour to babysit, and the amount of money earned in dollars is a function of the number of hours that she babysits. So, which of the following inputs is impossible? So, let's look at what is our input. Money earned in dollars is a function of time for the number of hours she babysits. So output is a function of input. So output is dollars, which means input is hours that she spent babysitting. I would argue that you cannot babysit for negative hours. You can babysit for 2 or 5 or 8, but it is only -1 that's actually impossible. Okay, so that brings us to question 7. The instructions for cooking a steak with a pressure cooker can be represented with this set of rules where x represents the weight of the steak in ounces, and f of x, or the function value at x, is the cooking time in minutes. So describe the instructions in words so they can be followed by someone using the pressure cooker. Okay, so let's break down what we have here. I like to kind of write what they're giving us. So this is the time in minutes. We always have our let me not get ahead of myself here. With piecewise functions, we're going to have an output and then conditions for our inputs in our sort of descriptions over here, because they're saying the function value at x is this. So we still have our function equal to an output value, and then it says when these things happen. So this one is minutes that you would cook it. And then these ones are the weight of the steak. So this is one of those situations where time is actually the output. I talk about with my class that time is almost always the input. However, there are some certain situations where time will be your output, and in this case, time is indeed an output because it's telling us how long to cook it for. So, this to me says if my steak weighs 8 ounces or 12 ounces or anywhere in between, I am going to cook it in the pressure cooker for 7 minutes. Then for steaks that are between 12 and up to 13, I'm going to cook it for 8. 13 and up to 14, I'm going to cook it for 9. 14 and up to 15, cook it for 10. And 15 up to 16, cook it for 11. So I do actually have a consistent pattern here, which means I can do more than just simply write out if your steak is between 12 and 13. I'm actually going to follow this pattern. I am adding 1 minute after a certain amount. So after I have 12 ounces, I'm then just adding on for each additional ounce about 1 minute of cooking time. So that's how we're going to word this, and that's how you'll see things often on cooking instructions. So we can say for our instructions, for 8 to 12 ounce steaks, cook for 7 minutes. Okay, now we have to describe our additional minutes of cooking time here. So it's only going to go up to 16 ounces because you don't normally get steaks above 16 ounces, but we can say for each additional, because that's how they'll put it on box instructions, for each additional, or in the instruction manual for this cooking appliance probably, for each additional ounce. We are going to add 1 minute of cooking time. There we go. And now we want to graph it. So we're going to start out with our 8 to 10. So those are the input ranges. I'm sorry, it's 8 to 12 ounce steaks. So for 8 to 12 ounce steaks, we're going to cook for 7 minutes. So I'm looking here on the weight. 5, I have 6, 7, 8. So from 8 to 12, which is just 2 past the 10 here, we are going to be at 5, 6, 7 minutes of cooking time right here. So that's the first thing I'm going to put in. And this did have solid, or what we call closed dots. So 5, 6, 7, 8. I'm going to go to 8 and then to 7. So because it had solid enclosed dots, I'm going to use a solid enclosed dot because they are using these symbols, which are less than or equal to. So if it's got one of those lines underneath it, we have to put a solid dot. If it doesn't, oops, switched over to the wrong homework assignment there. If it doesn't, then we are going to use an open dot. And so that would be like 12 here is going to use an open dot at this 8 level. So let's actually graph this out. So that is 8, 9, 10, 11, 12. So 2 solid dots here for our first level. This is the primary cooking instructions. For 8 to 12 ounce steaks, cook for 7 minutes. So this is 7. Then we're going to have 8, 9, 10, 11 as we go. And then, so at 12, it's equal to that. But anywhere between 12 and 13, we're actually going to add 1 minute of time. So we're going to zoom in here, and we're going to put an open circle at the 1 minute above mark with a closed circle at the next minute and connect. And we're going to do this for the next step as well, because adding 1 ounce, we're going to then add 1 minute of cook time. And we're also going to do this here. And we're going to go all the way up through adding those minutes on until we reach 16, and 16 is down here on the right next to 15. It's actually going to be my next step here. And we're going to check that this puts us at the right cook time for those things. So this said 15 to 16, cook for 11 minutes. Looks like that's what I have here for 15 to 16, but 15 not included in that. And we have to use the open circles because otherwise, if these were both closed circles, we would actually have an input that has 2 different outputs. So it tells us which one to actually pay attention to at this specific input value. It tells us which output we have to pay attention to. So that is our graph of our function. And yeah, we're gonna keep going. So that's 6 and 7. We have, I think, one last question here. So problem 8, because I don't see anything after that. We are going to look at absolute value. Well, you know what? We can talk about this, but we haven't talked about absolute value, so I'm not entirely sure if this one's going to end up on your homework because of that reason. So if this isn't on your homework, then thank you for joining me. But if it is, I'll still kind of talk about it anyways. That way you're not cut short. So absolute value of this function, q of x equals absolute value of x. It gives the distance from the 0 of the point x on a number line. So we're really just looking at a number line, and then x is on there, but we're just giving it the distance from 0. So we are using piecewise notation for it, where when we input an x value, x is going to be greater than 0. But if we have a negative x value, it's going to be less than 0. So determine if each point is on the graph. Oh, I'm sorry. This is when we input x, we get the same value of x if it's bigger than or equal to 0. Sorry. And if we also input x, we will get the negative value of x, or the opposite value, if it's less than 0. Because a negative times a negative makes a positive. So if x itself is less than 0, like negative 3, and we put in negative 3, this would become positive 3. So that's actually our first question, is inputting negative 3. We want to say it's not on the graph of Q. Change the output coordinates so it is on the graph. Well, at negative 3, it is going to change it into a positive 3. So we would say check mark or yes, it is on the graph, something like that. 0 gives the same thing. It gives 0 because it would return itself based on these instructions here. It says when x is greater than or equal to 0, it just returns the original value. And so 0, 0, we would say, yep, yes, this is okay. Negative 5, negative 5. Well, if I put in a negative, it should return a positive to me. So this one is going to be no, or not on the line. And it should be change. We're going to say change y value to 5, positive 5, or basically negative 5, comma 5. Just fixing that one part. Okay, for D, yep, this one is on the line because it would take a negative and turn it into a positive. And for E, this takes a positive and turns it into a negative, and that is actually incorrect. So we'd say no. Change we can change the negative 4 over 5 to just a positive 4 over 5, or change the y value to positive 4 over 5. And that's it. It's just basically testing if some of these points followed our rules over here based on this. So seeing if they work for piecewise functions, even though the idea of absolute value is kind of touched on in a different unit. So that is it for the Unit 1, Lesson 15, Cumulative Practice Problems for Illustrative Math, Algebra 1.